Okay, everybody, welcome back. Today's topic, we're starting glaciers. I thought we'd start with this nice photograph here showing it's a region on kind of a disputed area between India and Pakistan, and it contains a really large glacier right here, an alpine glacier, valley glacier, and you can see it running all the way down through here. And that's the start of it, the Siachen Glacier, world's largest non-polar glacier, 75 kilometers long. It's kind of like the third pole of the world. Lots of ice there, lots of stored fresh water. This is neat, 1870 postcard view of the Rhone Glacier in Switzerland. And you can see in the postcard, the glacier is much larger than it is today. Today it's shrinking back, perhaps due to global warming. Glaciers. Large masses of ice on land that flow under the pressure of their own weight. They can flow downhill or outwards due to gravity. Depends on the two types that we're talking about. Speaking of the two types, we have our valley glaciers. These are long, slow-moving streams of ice found in mountain areas, occupying former river or stream valleys. Or we have the big ice sheets, the continental glaciers. These are old, thousands of years old, thousands of meters thick, covering entire land masses. You've heard of Greenland and Antarctica, and these things are huge. You know, millions of square miles, kilometers thick of ice, a lot of fresh water. And you can get a view of the two types right here. We got the valley glaciers, or alpine glaciers, either way. And here's a continental ice sheet. You can see running all the way. There's the very edge of it, and it keeps running up that way. Sometimes the edges go right out over the continent itself and form shelves like Antarctica that can break off and form icebergs. And here's Antarctica and Greenland. Antarctica on the right, Greenland on the left. The scale here isn't really to true size or true scale. Greenland's much smaller than Antarctica, but you get the idea that they are covered mostly by ice. Thousands of meters of it. So most of the world's fresh water is stored right there. So where do they form? Well, glaciers form in either two places, high latitudes, near the poles, or high altitudes or elevations, where they have cold summers, cold enough year-round so that the ice sticks around. They presently occupy about 10% of the world's total land area, so not that much, compared to 1/3 of the world's total land area during the Pleistocene epoch. That's spelled incorrectly there, it's epoch. Here's a question showing how this all works. So we have a elevation on the right, we have latitude on the x-axis, and this line right here, the snow line, anything above that are the conditions favorable for glaciers forming. Below it, they don't form. So let's look at these potential answers here and figure out which one is correct. 15 north, 4,000 meters. Let's see if we get a glacier there. 15 north and 4,000 meters. Nope, no glacier. Okay, let's try the next one. 30 north, 3,000. 30 north and 3,000 is right there. Nope, no glaciers. 45 and 1,000. 1,000's right there. And 45, nope. And 0 degrees latitude, the equator, and 6,000. How could this be? 6,000? Yeah, there's actually glaciers that can form if it's 6,000 meters, 6,000 meters, not feet. And the elevation, it really does determine whether glaciers form or not, even if you're at a warm place like the equator. So it's interesting how that can be. In fact, I think in the last unit I showed you a photograph of Cotopaxi volcano, which was in Ecuador, and it had lots of ice on the top year-round. Here's just a nice view of the northern regions of the world, and you can see the United States, our farthest advance of ice during the last ice glacial period. In New York State, where I'm standing right now, was completely under ice. Lots of it. and the melting back that occurred the last 12,000 years till what we see today, leaving the Great Lakes, all these features behind, the Finger Lakes. All right, let's move on to the process of glacier formation. First, snowflakes. We know there has to be lots of them to make glaciers. And when they fall, just like around here at the end of the winter, they compact into this stuff called firn, which is, like the snowbanks towards the end of the winter. They're really hard, like packed snowballs. So the snowflakes accumulate. Eventually, the lower layers turn into glacial ice. And the more they get smushed, the more air gets pressed out. It becomes kind of a bluer ice under the weight of overlying firn and snow. You can see a snowflake here changing shape over time into ice. And obviously more snow must fall than melts. Now the place where that happens we call the zone of accumulation. It's in the upper part of a glacier where it snows more than it melts. Now at the other end of the glacier, it's called the zone of ablation or zone of melting. This is the lower part of the glacier where it melts faster than it grows. And the line between them, like that question I showed you earlier, is the snow line. It's like the equilibrium line where the snow is all year round above it, but not below it. Okay, next question, how do glaciers move? Well, we know that they move under their force of their own weight by gravity, pulling on them. That's the driving force. Now under pressure, you got a lot of weight of ice above, the lower parts of the ice starts to behave like a plastic, a thick fluid. And it will actually flow without cracking. And it moves downhill in the case of alpine glaciers or spreads out in all directions downhill in the case of continental glaciers. And it takes some pretty thick ice for that to happen. So glaciers will advance forwards, move downhill or grow if snowfall is greater than melting. They'll retreat if snowfall is less than melting. And if it's stationary, snowfall is equal to melting. This is not rocket science. They call that a dynamic equilibrium. All right, let's take a look. So here we have getting colder, wintertime, it grows. In springtime and summertime, it shrinks. So your glacier overall remains about the same unless climate changes, unless it gets warmer, in which case the glacier will retreat more, or colder, in which case the front of the glacier will grow more. Important to note that ice within a glacier is always going forwards. It's always like a conveyor belt pulling ice downhill. Even if the glacier is not retreating or stationary, it's still moving forwards. It's just not going to look like it's moving forwards because the very edge of it is melting backwards sometimes. Now I mentioned before that glaciers are like rivers or streams of ice. Just like water rivers and streams, glaciers do flow faster in the middle and slow on the sides. And this is simply because of friction. There's less friction in the middle. And they flow faster after heavy winters, down steeper slopes, and when they get a little bit warmer and more fluid-like in the summer. Now, another thing that glaciers form, because the top is more brittle than the bottom, it's under less pressure, the top part will slide over steep parts in the terrain below it, forming crevasses, which are these deep cracks. Wouldn't want to be that skier there. So here you can see some mountaineers. They're connected by rope, they got their ice axes, all the tools of the trade. They're harnessed together, their glacier goggles, their helmets, and they got to watch out for those crevasses, which can sometimes be covered by snow after a nice snowstorm. One way to get over crevasses, a brave way, but necessary, I guess, is using aluminum ladders and ropes. You could even rappel down into the glacier or into the crevasse. Maybe he dropped his glasses and he's going down to get them. And here you can see a large crevasse field. And you'll also notice that the snow is dirty, the ice is dirty. And that's either from the rocks that it's carried downhill, or it could be from pollution or soot from the sky, or for perhaps a volcanic eruption or something. But the darker that snow gets, the faster it's going to melt. Here we have the glacial terminus. This is an area of the glacier where it's still bringing ice down from up above like a conveyor belt. And this area will be unsorted. The rocks there will be all different mixed sizes and shapes underneath that ice. And out in front of us here in the foreground is the outwash plain. In this area where glacial meltwater is carrying sediments, it'll carry the smaller sediments farther than the larger sediments. So it actually becomes sorted by size. We'll learn more about that later in the unit. Here's a bird's eye view of a glacier, just to show you how it moves faster in the middle than on the sides. Friction on the sides slows the glaciers down. So the fastest is in the middle. And you can see that right there. The bottom is slowed down by friction. The top of the glacier moves faster because there's less restriction there. Here you can see a continental glacier that builds up in the middle and it flows outwards to the sides, sometimes going right over the edge of the continent, breaking off, forming icebergs. It's kind of like silly putty. If you left a big ball of silly putty on a desk overnight, when you came back the next day, it would be flattened right out. So here's another question that you might run into on one of my quizzes or tests. Wooden stakes were placed in the glacier in a straight line represented by AA prime. The same stakes are observed later and represented by BB prime. What happened? The pattern of movement of the stakes provides evidence that, and you're looking for an answer that has to do with moving faster in the middle, less friction in the middle, or more friction on the sides, something like that, like answer 3. They don't say exactly why it's moving faster in the middle, just that it is. But you know why. Okay, this question, I would always look for a more even kind of curve in the stakes. So we're looking for something like this, not something obviously that's all whacked out like that, or barely moves like that, or like this. And these three perhaps are moving even in the wrong direction. Usually glaciers widen out towards the bottom and are narrower towards their tops. So this would even be going the wrong direction in this picture. This one has 2 directions, that's not right. And this one would be going the wrong direction in this picture. So this answer makes the most sense. And that is it.